I thought I'd do a quick video on putting together the QRP Labs 10-watt linear amplifier, and I'll include a link below where you can get one of those from. This is a HF amplifier suitable for single sideband, CW, and various digital modes, and it consists of a two-stage amplifier. The first stage being a pair of BS170s, which you can see here, and then there's a second stage which consists of a pair of IRF510s. And both of these are configured in a push-pull configuration. The schematics right here. So this is it's a pretty small little kit, but a fun one nonetheless. And let me just walk through kind of the various high-level modules in the circuit. And as usual, when I'll be building this up, I'll kind of do it module by module. So 1, 2, 3, 4, 5, and so on and so forth. So part one is the power supply and bias supply for both the BS170s and the IRF510s. The bias voltage itself is turned off and on by this P-channel MOSFET here. So when this line here is grounded, that turns this MOSFET on. When it's open, this MOSFET is turned off. Part two is it's an interesting circuit, and I've seen this quite a few times in circuits that have a pair of BS170s and push-pull. And its primary purpose is to provide a bias reference through to the gates of the push-pull BS170s. Now, these two BS170s are thermally coupled to this BS170 here, and I'll show you that on the circuit later on. But basically this transistor, and this transistor are all connected to the same heatsink. Now, I believe the purpose of this is to have thermal stability around the gate voltages of these BS170s, so that it doesn't drift as this heats up. Now, that's my belief. I haven't been able to find a real reference to this. So although this circuit is used in a lot of places, I haven't actually found a good circuit description. So if anyone has seen one of those, I'd love to see a reference from you. So then moving on, stage 3 here is the input splitter, and we've seen this a lot before in kind of some of the videos that I've done. It consists of a binocular core here, and the signal comes in here and is split into phase and antiphase, which is then applied to the gates of the BS170s. Now, one of the interesting things about this circuit is it's not 50 ohms input. And again, there's a reference to this on the QRP Labs site, but it varies. And so it's around about 400 ohms at 7 megahertz, going down to about 260 ohms at 14 megahertz. And then it doesn't get down to 50 ohms until right up at 10 meters. So it's something to bear in mind there. Hans does mention that if your input circuit is sensitive to that, then he suggests putting a 75 ohm resistor in parallel to the input here. But just something to note, this isn't a 50 ohm input. So moving right along, part 4 is the amplifier first stage, and as I mentioned, it's the pair of these BS170s in a push-pull configuration. Power comes through this RFC here, so ultimately this guy's connected all the way over here, so power comes through here, and note that power is always there whether the transmitter is turned off or on. So it comes through here and then is applied to the center tap of this T202, which is another binocular core toroid here. Then finally we have the amplifier second stage, and this is a very similar circuit to what we saw with the QRP Labs 50-watt amplifier. I mean, obviously a little bit different here, but just to highlight some of the differences, unlike the 50-watt amplifier, which had a single bias source, this amplifier has two independent bias sources here, and that's controlled by these two pots, R211 and R215. So you can set the bias voltage to the gate of these two transistors independently. And then this circuit here is very similar to the circuit that's in the 50-watt amplifier. Power is applied through here, and then we have this final combiner here, and then the output power here. And the output is actually a 50 ohm output. And one of the things to bear in mind is, obviously you'll see what's one of the things that's missing on here is there's no low pass filter on this circuit. So if you want to be legal with this, you do need to have a low pass filter after this that's specific to whatever band you want to transmit on. So anyway, yeah, so, we can certainly do testing on this without the low pass filter there, but we don't want to get it on the air without a low pass filter. It will emit harmonics. So as usual, I'll be going through each of these modules in order, 1, 2, 3, 4, 5, and we'll be doing a bit of testing, or the testing that we can do after each of these modules. So we should be able to see, for instance, after the first one, that we're getting the correct bias here when this is grounded. After the second piece, we should be able to look at this bias voltage here and confirm that that's the correct bias voltage. And I believe that's, in this circuit, that's around about 10 to 11 volts. Well, once we do part 3, we'll be able to apply an input signal, and we should see the phase and antiphase signals at applied to the base of the BS170s. Then we can put this part of the circuit in, the first stage. And again, once we put these 220 ohm resistors here, we'll be able to tap off here and here, and we should see an amplified signal here. And then finally, we've got the final stage here. Once we get that installed, we'll be able to see the output signal with all those harmonics. So we'll actually get to see that. So that's the plan of attack here. Just before we move on to that, though, let's just have a look at the kit itself. Let me pan down a bit. So here's the kit. You can see it's very small. This is the primary circuit board here. And what you do also get with the kit is this fairly beefy heatsink here. So you can see here, the holes are already drilled, ready to go. These are the two IRF510s, and so that the actual circuit board goes on top, and then the IRF510s are underneath and thermally coupled to this heatsink here. So I'll get on with that. We'll build up the power circuit first, and then come back and do some testing. Just a quick note to be aware. I usually do this warning. I'm actually doing the kit out of the order that Hans recommends. So that's the way I like to do it. So I find it more fun that way. But definitely the instructions in the kit are very clear, and are more for, I think, as someone said, for convenience than for learning. So anyway, I'm building it out of order. So some of the stuff will be a little bit different to the instructions in the kit. So anyway, let's get on with the build. Okay, so here's the power supply circuitry installed, and just some build notes. I actually got a 70 mic cap in the kit, not a 100 mic as on the schematics. Obviously you have to observe polarity of that. Just moving over here, so here's the bias off-on circuitry here, which consists of that P-channel MOSFET right here. There's a 5-volt voltage regulator, a 10K resistor right here, and then finally a little smoothing cap on the output of that. So what I'll do now is just test to make sure we're getting the right bias voltage on the output here, and then we can move on to the next stage. Okay, so just back to the schematic. What I've actually done is installed a little switch here that grounds TX line here, and then what I should see is when I ground TX, I should see that bias voltage come out here, and that bias voltage will be 5 volts direct from this regulator. So I can tap off this bias voltage in a number of places. A convenient one is the gate of Q205, so that's where I'll be probing. Okay, so the switch is currently turned off, so let's check the voltage. So here's Q205 right here, and then this is a convenient ground right here, so you can see the voltage in there is close to ground. So let me flip that switch on, and we should see the Q205 be around about 5 volts. So let's be careful here. Make sure you can see what I'm probing at. So there's Q205 base there, and you can see that's 5 volts. So that confirms that that input switch is working correctly. So we can move on to the next stage now. So just a reminder, this is the next stage, and that's that bias reference circuitry. So I'll pull all this together here. and the end result is when we enable the transmit switch that I've installed, we should get the BS170 bias out here, and I believe that should be around about 10 or 11 volts of bias, but we'll see that. So again, the circuit here, this is that reference circuit that I said that if anyone has a reference for the reference circuit, I'd love to see it. And then this piece of circuitry here is simply when the bias voltage is applied here, it grounds the gate of this P-channel MOSFET, and 12 volts then flows through here. So this is just another input switch here against 12 volts. Anyway, so I'll pull this together and then we'll do some follow-up testing. Okay, so I've put the bias reference circuit together. So that consists of this pair of MOSFETs here, which switch the 12 volts into the circuit based on this bias here. And if we could just zoom into that, you can see. So here's that P-channel MOSFET, and then here's the associated BS170 that turns this P-channel MOSFET on. And then, you know, for the rest of the circuit here, you've got a MOSFET here. That's this MOSFET here, and this is the one you have to be careful about the orientation. So basically what it is it's the flat side down. So this is this trio of MOSFETs that I mentioned before. These two places here are for the push-pull pair, and then this MOSFET here is used to sort of set a reference bias. And the idea is, I think the idea is basically, so you put a heatsink over the top of all three here, and then these three are kind of thermally coupled. So as the temperature rises, the gate reference also rises. At least that's my understanding of it. I like I said before, I haven't seen a good write-up of this circuit to dig into more. Now, one of the other things that I had to do is you can't just include this part and then just panning over, and then this part here, because otherwise there isn't an appropriate ground for this bias here. So what I have to do is just to create that path to ground for this spot up here, I installed this R211 variable pot here too. So even though it's not really part of the circuit I'm going to test, I kind of needed it to provide that path for this guy to ground. Was getting some strange results. Incidentally, I actually installed this the wrong way around to start with, and it blew up the BS170. So that's part of the joy of not reading the instructions properly. So anyway, I've got lots of spare BS170s, so that wasn't a problem. So anyway, let's move on to testing the circuit. Okay, so I'm ready to start testing, and the test points that I've got here is there's this 33 ohm resistor here. So this is the multimeter lead here, attached right here, and then I've got the red lead attached right here on the cathode of this diode here, and that will be the voltage that's actually presented down here to the center tap of this here. So let's check that out. So I've got it. I've got effectively TX as open circuit at the moment, so this is not transmitting, so it's 0 volts. And then if I turn transmit on, it's 2.76 volts. I'm not sure why I was thinking it was around 10 volts, but I did check on the other circuit that uses this, the RX-TX ensemble, and 2.7 volts is the correct voltage at this point. And that's the voltage at which those two BS170s in the push-pull just start to turn on, around about 3 volts. So anyway, what that does is it confirms that part of the circuit is working correctly. I can move on to the splitter next. Okay, so next I'm going to move on to this input splitter here, and that's pretty simple. It's this binocular core right here with 6 turns on the primary and then 3 turns bifellow wound, and then these two 220 ohm resistors right here. So I'll wind this together and then we can inject the signal in here and we'll see phase and antiphase coming out of here. So here's the binocular core right here, and one of the things that that you're advised to do is sort of remove any of the, you're not quite in focus there, so remove any of the burrs on the edge of this. So you can either do it with the drill bit or just do it with, I'm using just a Dremel attachment here to do that. So obviously you do it by hand, you don't do it with the Dremel itself. So, and that avoids scoring the enamel off the wire. So anyway, I'll wind that and we'll come right back. Okay, so I've created some bifiller wound wire here. There's actually enameled wire that comes in the kit, but I like using this red stuff. So this is 30 gauge. I tried 28 gauge and it was too thick. I couldn't get it all the way through. So the way you wind a binocular toroid is each time the both wires pass through the center, that counts as one turn. So it's a little bit different than a kind of a standard toroid there. So I'll wind that, get that on there, and then we'll come back. Okay, so I've actually wound both the primary and the secondary there. You can see that it is kind of a tight fit. There's a little bit of space left. You can just see it there through the center there. So you definitely wouldn't want to go any thicker gauge. And this was 30 gauge. This is 30 gauge here. And this is 32 gauge, and this is 30 gauge. So I probably would have been better off doing 32 gauge on the secondary as well. So now the good thing though is these are different colors, so it's going to be easy to tell them apart. So what I'll do is the next step is to sort of remove the enamel on both sides, and then we'll be in a position to install it onto the circuit. Okay, so now we're getting ready to install T201 here. So this is kind of the fun part. Let me get the camera here. So T201 goes right here, and the way it goes is these 4 holes here are for the bifiller, and this guy matches this guy, and this guy matches this guy. So when you sort of beep it out, these two should have continuity, and these two should have continuity. And then finally the primary is the bottom two. So now when you get this in circuit, it's kind of impossible to check it. I mean, you can check to make sure that there's no continuity between the primary and the secondary, but you've got to make sure that you check the toroid beforehand to make sure you get the so-called A and B windings on the secondary correct. So anyway, let me get that done and I'll put it on the circuit. Before I install it in the circuit, I'll just sort of show the order of the wires. So these 4 wires at the top here, these are the 2 bifiller windings, and then this is the primary single winding here. So just getting them ready for the order on the board. These 2 should have continuity. Let's make sure I'm not touching the other one. These 2 should have continuity, and then these 2 should have continuity, and then finally these 2 should have continuity. So that's ready to get installed on the board, and it goes just like that with the 2 bifiller windings at the top and then the single primary at the bottom. Okay, so there's the toroid installed, and it all looks okay. One thing you've got to be super careful about checking, particularly on the secondary windings, so that's the windings up the top, is that you haven't crossed any of them over and caused a short between the secondary windings, and that does not appear to be the case here. So obviously the easy part is to I'm not getting very good focus here, unfortunately. Bear with. Yeah, so those secondary windings are definitely separated. So that's something definitely to check. I mean, obviously, if you haven't got them connected correctly, it'll show up when you're doing the testing on the phase and antiphase. You'll get some. You'll probably get nothing out on the secondary if you've got them crossed over incorrectly. But anyway, what I'll do is I'll solder that in and then put the 220 ohm resistors in, and then we'll be in a position to test an input signal. So that's all installed, and what I'm going to do now is probe actually right at the gates of these yet to be installed BS170s, and just to show you that right here. So let me zoom in a bit so you can see that a bit better. Oh, bear with me, hang on a sec. All right, so there's the two oscilloscope probes, and they're right at the middle pins of the of these two BS170s that are here. And I'm injecting a 7 megahertz signal at 1 volt peak to peak. Bear with me while I just move some stuff around here. And there you can see that nice phase and anti-phase signal on the oscilloscope here. So obviously it's 7 megahertz, and then probing those two different gates on those BS170s gives us that phase and anti-phase signal. So the T201's installed correctly, and we can continue to move on. Sort of actually done, just before I move on, I've got the probe set up in the same place, but now I'm injecting that bias signal on there, so you can see when I turn it off, that's off, and then when I turn it on, you can see it there, it's biased at around about 2.7 volts, and you can see the minimum and the max is from 2.93 to 2.51 volts. So kind of confirms that bias is set up correctly for those two BS170s. So anyway, what I'll do next is move on to the BS170s themselves. Bear with me, let me get this shaky camera in a good spot. So we've installed up to here these two resistors. We've probed at the gates of the BS170s and confirmed that we're getting a good signal there. What I'll do now is I'll move on to this section here, get those two BS170s installed, get this combiner installed. There's an RFC to install up the top there, and a couple of caps, and then we'll be able to probe here and here, and we should see an amplified signal out of this push-pull arrangement here. So that's coming up right next. So just before we move on here, just some quick housekeeping. I looked back at the instructions, and these two 220 ohm resistors here and here should be of the half watt variety, not these quarter watt resistors. So I'm not going to pull them out at this stage, but I will monitor them to make sure that they're not getting too warm. So anyway, just a note for builders, this resistor here should both be the half watt 220 ohm resistors, not the quarter watt ones. Okay, so I've started to wind T202. This is 3 turns by filler and 5 turns on the single winding there. So because it's an odd number of turns, you start it with it going through that way for the 5 turns, and that way you'll end up 1, back out 2, 3, 4, 5, because you want the wires coming out the same side of the binocular core. But anyway, I'll get on with that and then install it on the board. Okay, so here's where T202 goes right here, and it's kind of the same arrangement as the other binocular, in that these two rightmost holes are for the secondary, for the bifiller winding. So this should have continuity with this. This should have continuity with this one on the bifiller wound, and then this is the single winding here. So these two obviously should have continuity. What I'm going to do is I'll remove these test leads that I had before, and I'll install resistors 207 and 208. They're the 2.2 ohm resistors that are on the from the source of these two MOSFETs to ground. So I'll install those. I'll remove this, and then I'll install this guy, and then finally the MOSFETs. Okay, so there's that installed but not soldered in, and as you can see, these wires are super close together, these secondary wires here. So these are clearly not touching, but over on the other side it's a little harder to make out whether they're touching or not. And This is kind of one of the challenges is all these secondaries are actually connected in circuit, so it's impossible to tell when it's in circuit whether they're actually touching or not. The only way to find out is to actually inject a signal in there and see what happens. It'll be obvious from that, but it won't be obvious by just buzzing it out on your multimeter. Anyway, I'll get that soldered in, and I'll get these two BS170s and continue. All right, so there's the BS170s installed. Note orientation, they're all face down. You can't, if you get it all face down, you can't muck it up like I did earlier. So that's the two 2.2 ohm resistors in. Here's the RF combiner. Here's the push-pull BS170s. What remains is there is an RFC that goes here, which is another binocular core. And there's a cap, a 10 mic cap, and then there's a smaller 0.1 mic cap. And that connects this, the center tap of this toroid, binocular core here to 12 volts. So I'll get on with that, install that, and then we'll be in a position to start doing some testing. Quick note that might be of interest to people. So there's two types of binocular cores in the kit. There is a BN43 2402 and a BN61 2402, and they look pretty much identical. But if you mix them up, there is a way of figuring out which is which. So I have the 43 on the left here and the 61 on the right. And as you can see, it's a little hard to see, but the 43 has a shiny appearance and the 61 has a sort of a dull appearance. And it can actually look sometimes like there's a bit of rust on it. But that's the way to tell them apart. So here's the 43, shiny appearance. Here's the 61, a duller, flatter appearance. Anyway, I thought that might be of interest. All right, so that's that RFC installed right here. That's the BN43, the shiny one, if you'll remember. And then there's these two caps, a 0.1 microfarad cap right here, and then this electrolytic here. And just note the polarity, the negative is on the right-hand side, positive on the left-hand side. So that pretty much completes this part of the part 4 of the circuit here. Bear with me, let me just zoom out a little bit. So that completes, we've got this installed, we've got the two BS170s installed, the two 2.2 ohm resistors, and T202, the combiner. Now the final thing, in order to sort of present a correct impedance to this stage, is to install these two 220 ohm resistors, and these are the half-watt resistors. So these are the same sort of half-watt resistors that I should have installed here, but I didn't. So I'll get these two half-watt 220 ohm resistors installed, and we'll come back. Okay, so those two 220 ohm resistors are in place there, the half-watt variety. And note, if you want to use them as a probe point, make sure that these flying leads go to the inside, so up and to the inside. But anyway, I'm probing them, and let me move up to the oscilloscope so that you can see these signals on the oscilloscope. There we go. So let me flip the switch and we'll see what we see. So there we go, nice phase and anti-phase signals. That's a 1 volt peak-to-peak signal on the input, and we're resulting in a 4.2 volts peak-to-peak signal on the output. Now I'm being quick here because I actually don't have those BS170s heat sinked yet, so I don't want to overload them here. But anyway, that's I'm not sure what the expected peak-to-peak is for that first stage, or expected gain for that first stage. I'll probably have to look at that separately. But what we're ready to do now is move on to the final stage with those two IRF510s. But anyway, good progress. Okay, so moving on to the second stage of the amplifier. So what I'm going to do is, I've already installed this pot here. I got that installed earlier. So what I'll do is I'll install kind of the bias setup circuits here and here, and then I'll confirm that I'll put a test point here and confirm that we're getting that. It should be from 0 to 5 volts applied at the as a DC bias applied at the gate of these IRF510s. Now the IRF510s, the install themselves, it's you install them from underneath the board. So that's a bit of an interesting part to the build. So I'll cover that separately. But let me get all this installed here, and then we'll come back and test that DC bias on the gates of both of these. All right, so all the DC bias circuitry is installed for the 2 FETs here. So that consists of a couple of caps. There's an inductor here to keep RF off the power supply. Obviously, the 2 pots themselves, and then there's a 47 ohm resistor also. So the gates for each of these FETs are this pin here and this pin here. So this goes gate, drain, source. So source is connected to ground in this configuration. So what I can do is probe between here and here, and that will get me the DC bias on the gate. Now with these pots, fully counterclockwise is minimum bias, fully clockwise is maximum bias. So we'll be able to see, I should be able to go from 0 to 5 volts on the gate there. So anyway, I'll get that set up and then we'll come back. So checking the bottom one now. Now I've got that the pot turned fully clockwise. So there's 5 volts on the gate there. Let me turn it all the way counterclockwise. Bear with me, a lot going on here. That's fully counterclockwise now. And turning the switch on, 0 volts. So that gives me that full range of 0 to 5 volts on for the DC bias of the IRF510s. So moving on, what we're going to do now is basically install the rest of the circuitry. There's not much more sort of intermediate testing I can do here. These are the 2 IRF510s. This is some stability circuitry right here, and then there's a bifiller wound T5043, and then finally a 2-turn, 3-turn BN43 202 left to wind. There's a couple of caps here as well to install, and then we'll be able to kind of put a 50 ohm load on the output and check what we're getting. Okay, so a bit of explanation here on how the IRF510s connect to the board here. And basically what it is you bend the leads up like this, and then this gets placed flat against the board with a sill pad in there to insulate it from the heatsink. And then you basically put the leads through like that, and then you line it up with the holes underneath, and that's how it goes. So it's a bit fiddly, but pretty straightforward. And now obviously this heatsink here, so this is the trio of BS170s right here, that goes into this hole here, and there's a little M4 nut that acts as a standoff in that hole. So that's basically how it's put together. And so what I'll do is I'll include all of this circuitry here, and I'll put the FETs on. I'll wind these transformers, and we'll be on the way. So here you can see I've got the IRF510s partially installed on there. So we have the sill pad at the bottom here, so that insulates the body of the IRF510 from the heatsink, and then we have this screw here and an insulator between the screw and the body of the IRF510. So I'll screw that on and then come back. So here's the semi-finished product here, and you can see there's the sill pad between the IRF510s and the body of the heatsink, and also you can see here's the other. Here's the trio of BS170s here, and then there's that M4 nut that acts as a standoff. And inside the M4 nut is actually a piece of plastic to, again, insulate the, just to make sure that that nut doesn't move along. So note that this isn't soldered in yet. The idea is you get this all lined up and then you solder it in. If you solder it in first, you could get out that this is misaligned or what have you. So what I'll do is I'll basically solder these guys in, and we'll come back. Okay, so that's those two soldered in. Now, one thing to watch out is this lead here and this lead here are connected to ground. So depending on the wattage of your soldering iron, that might be a bit problematic. So if you get into trouble there, just simply solder the top two and then unscrew this, pull it off the board, and then solder the remaining source lead on. I've got a fairly high power soldering iron, so I didn't encounter that problem. So the other thing too is this is now connected in there fully. I do have to put a sill pad between this washer and the BS170s to complete that side of it. So just a quick update. Basically got everything on the circuit except for the two remaining. This T5043 here, bifiller wound, and then this final binocular core right here, which is the kind of the final output RF combiner. So once I put this and this guy on, we'll be pretty much done. Obviously, I'm just going to put a little kind of pigtail on here with a BNC on it so I can tap the output and see what that's like, feed it into a 50 ohm load, and we'll see what happens. So I found the instructions a little bit confusing in the manual about what you're supposed to do with this bifiller wound, but basically the situation is you have the start of the winding on one side and the end of the windings on the other side, and then you have the start of the first winding, start of the second winding, and then crossing over end of the first winding, end of the second winding. So that's basically how it goes on the board. So both windings out of the same side. So these are both the starts. So that's the start one, start two. And then on the other side, this is end one, end two. So we should have continuity across these here. There's a continuity there. So, excuse me. Let me just get that back in there. Doing this behind the camera. There. So that's continuity across like that. And that's how it goes into the board. Okay, so that's that T5043 installed. And, you know, again, this is one of these situations where once you've installed it, there's no real continuity tests you can do. So you've got to check it before you install that there's continuity between this side here and its opposite side over there, and from here to here, and that's how it goes in on the board. Anyway, there's only one left, one binocular toroid to get installed, and that's this right here, and that's a simple two turns on the primary to 3 turns on the secondary on the output, and so I'll get that installed. And it's right here. This is the final piece of the puzzle. So that I'm just gonna wind with some red and green wires and get that installed on the board. Okay, so there's the final binocular core wound there, and I've chosen green for the 2 turns, which is the primary, and then red for the 3 turns, which is the secondary. So I'll get that installed on the board and we'll proceed. All right, so we're just about done here, just doing some final tests here. So I've got this connected up to my power supply here, which is a bit beefier than the other power supply. On the oscilloscope here, let me just turn trace 2 off. I'm probing the output, and I've got the output also connected to my little watt meter here, just to see what we're getting. And so let's turn TX on. Oh, also I am injecting a 14 megahertz signal, 7 volts peak to peak on the input there. So that's all set up. Let's turn it on and see what we get. So you can see there about 9 watts of output there, but take a look at that, all those wonderful harmonics. Let me zoom into the oscilloscope here. So you can see that. Bear with. All right, let's check that out again. Look at all those wonderful harmonics there. So it's 14 megahertz. I mean, that's the fundamental frequency there, but as you can see, there's no low pass filter after the amplifier, so you're going to get a raft of harmonics at 28 megahertz and 42 megahertz and so on and so forth. And I'll actually hook it up to the spectrum analyzer so you can see all those harmonics. And that's why this amplifier without a low pass filter isn't ready to go on the air yet. So let's just zoom in again. Just onto the adjustments themselves. So let me zoom into the kit itself. So here's the positions of the two pots that ended up working for me. What you're supposed to do is you connect it with them fully counterclockwise, and then you measure the current consumption from the power supply, and then you slowly bring up the top one till you get 125 milliamps above that. And then when you're good with that, you bring up the bottom one to 125 milliamps above that again. So mine started at about 50 milliamps, and then so at the end, sort of, I guess, quiescent consumption of current was about 0.3 of an amp there. So let's just zoom out again, and we'll do that one more time, and you can see how much current it's actually consuming. You can see there 2.1 amps. This is not even warm. So that's interesting. What I'll do now is I'll move over to the spectrum analyzer, and we'll be able to see all those wonderful harmonics. Okay, so I've got that input into the spectrum analyzer going through a 50 dB 30 watt attenuator. So let's click on transmit again. Look at all those wonderful harmonics, and you can see there this is 14, 28, 42, and so on and so on. 42 plus 14, so 56. So lots of interesting harmonics on the output there, and you can see it if you put that on the air. That would definitely make you FCC not legal. So anyway, this has been a fun little kit. I've quite enjoyed putting it together. I hope someone else finds the construction tips useful. A lot of fun kit. Highly recommend any QRP Labs kits. They're a lot of fun. Anyway, that's a wrap for now.